Chapter 6 talks about gases. So in this chapter, we're going to talk specifically about gases and kind of some of their properties and their relationships, like between things like pressure and temperature and volume, and so on and so forth. So before we get into talking about that, I just want to kind of review kind of what we know about gas particles and how they behave. So gases are going to be molecules or atoms that are going to move randomly and rapidly, so they're kind of floating around and they're moving in all kind of different directions. And the area between gas particles is going to be very large. So the idea is the gas particles themselves are small and the area between them is large. And because of that, they're going to be far away from each other and they're not going to exert attractive forces on each other. Or if they do, they're going to be very weak. Another important point here is that the kinetic energy of gas particles increases with temperature. So whenever you heat a gas, the particles move faster and it gives it more energy. And then last point on the slide here says that when gas particles collide, you're going to rebound and travel in opposite directions or new directions. So again, this is just talks about what's referred to as the kinetic molecular theory of gases and talks about how they move and how these gases behave. Now, whenever we're trying to do measurements with gases, typically we measure kind of the pressure of a gas. So the idea here is that when a gas, I'm going to draw a little picture. So if you have a ball or a sphere or a balloon or whatever it is, and you're going to have gas particles in there, right? So these are our little gas particles. They're moving all around. So they're going to move in these various directions, right? And I'm just drawing these arrows to show you how they're moving. And then whenever they hit the walls of the container, they're going to exert a force against that container, right? So we can say that the pressure of something is going to be the overall, that force divided by the area. So if you had a smaller circle, and you had those same four particles, right, and they're still going to be moving in the same directions, because now you have a lower area, the force is going to be higher. So, right, the smaller the area, the higher the pressure is going to be, assuming that that force stays constant. We can measure the pressure of things in a number of different units. Atmospheres is going to be one we look at a lot, 1 atmosphere. And the other two that we're going to look at, or you're going to see quite a bit, is going to be millimeters of mercury, or 1 atmosphere, 760 millimeters of mercury, or also a torr, which is the same thing as millimeters of mercury. So you can also say 1 atmosphere is equal to 760 torr. PSI is pounds per square inch. This is kind of like frequently used whenever you're measuring like pressure in your tires, right, for your car. Pascals is the one down here at the bottom. That's another unit. These ones, you can see it's 101,325 pascals per 1 atmosphere. So a lot of times you'll see, you'll see this written as kilopascals. So in other words, you could also write 101.325 kilopascals, right? Because of using our metric prefixes, we could also say that. The ones you need to really be most concerned about, though, are the atmospheres, which is abbreviated with ATM, and millimeters of mercury and torrs. And the relationship between those is 1 atmosphere per every 760 millimeters of mercury, or torr. All right, so in looking at the gas laws, so the gas laws are basically a number of different ways to describe the relationships between parameters of the gases. So if you look through your book, there's kind of they go through these different gas laws one by one by one by one, and there's basically 5 different gas laws. You can look around here, like Boyle's law, Avogadro's law, Gay-Lussac's law, there's a combined gas law, and Charles's law. They all relate to what is referred to as the ideal gas law, which says PV equals nRT, where P is the pressure, V is the volume, N is going to be the number of moles, or the amount of gas, T is going to be the temperature, And then R, I skipped over because it's a constant and it never changes. So R, if you look up here in the upper left, is going to be a constant, so it's always going to be the same. And there's two different constants. There's 0.0821 liters times atmosphere divided by moles times Kelvin, or 62.1 liters times torr divided by moles times Kelvin. So how do you know which R you use? Well, it depends on if your pressure's in atmospheres or if it's in torrs. And remember, torr is the same thing as millimeters of mercury. So those two terms are interchangeable. So you have both of those gas constants, right? That's kind of provided to you on your exam sheet and things like that. So you just have to know which one to use. Now, the one other thing I want to point out is that the unit in R for temperature is always going to be in Kelvin. So just like we've always done, your units have to cancel each other out. So whenever you're doing anything with gases and you're reporting a temperature, the temperature is always going to be in Kelvin. So if you think back to chapter 1, I told you need to know how to convert temperature to Kelvin. This is why, right? So all of our temperatures always have to be in Kelvin. All right, so if you look through on this slide, it's very busy. There's these 6 different equations starting all at PV equals nRT and then 5 derivatives from that. You do need to know these equations and how to use them. I don't care if you necessarily know the names. I'm not going to ask you Boyle's law and expect you to know that it's P1 V1 equals P2 V2, but I will expect you to be able to solve a problem talking about how pressure and volume is related to each other. So you can always come back and memorize these formulas, but what I'm going to do is I want to go through and kind of explain how these laws can be visualized, and then I'm also going to talk about how they can all be derived directly from this equation. All right, so Boyle's law, constant n and constant t. So again, we're going to start with this PV equals nRT. So we know that in Boyle's law, if n is constant, T is constant, and we know that R is always constant. So all 3 of these things remain constant. So that tells us the 2 things that have to change in Boyle's law are going to be P and V. Those are the 2 that vary. So you can see in my 2 pictures here, right, I have volume here is going to be smaller than the volume here. So in other words, the volume increased between the 2. So the question is what happens to the pressure? So what I'm going to want to do is I want to go into this first one, and let's again draw these 4 molecules of gas that are floating around. All right. So, and again, constant n means constant number of moles of gas. So here I have 4 moles. Pretend each of those dots is a mole of gas. They're going to be moving around, exerting force on the outside of the wall of the container. And now, if you take those same 4, because we say it's constant, we're going to move them down here to this one. And also with the temperature being constant. So the temperature being constant means they're going to be moving just as fast. They're going to have the same amount of energy. Well, they're going to be moving. However, now whenever they're moving, they have to move further before they hit the walls. So what's going to happen is that as the volume increases, the pressure is going to go down. So volume goes up, volume goes up, pressure goes down. So you could also say that they are inversely proportional. Okay? So the idea here is that these molecules are still moving and they're moving with the same speed, but because the volume is bigger, it's going to take them longer to hit the walls. That's going to cause a decrease in pressure. So that's Boyle's law. The next one to look at is Avogadro's law. So Avogadro's law says constant P and constant T. So in this case, the ones that are going to change are going to be N, so the number of moles, and we're also going to change the volume. So again, you can see that the volume in my 2 circles here has increased. So let's go through, and in the first case, let's make it just like the one we did on the left. So it's going to look the same. So here are the gas particles and they're moving. Okay, so now in the one in the bottom, right, we want to keep the pressure constant. And we know that if we have the same temperature, the molecules are going to be moving at the same speed. However, keep in mind here with Avogadro's law, n is going to change. So what's going to happen here is we're actually going to end up with more molecules of gas. So now whenever they move, you have more molecules of gas moving. Now they're moving at the same speed, but because there's more of them, they're able to increase the amount of pressure, or again, not really increase the amount of pressure because the pressure stays constant, but there's more pressure that's going to be found within that within the sphere in order to keep the pressure constant to make up for the larger volume. So in this case, volume goes up, and then the number of moles also has to go up. So you would say that these are going to be directly proportional. All right, so whenever they both move in the same direction, you say they're directly proportional. If they go in opposite directions like they did over here, we say they're inversely proportional. Okay, so volume goes up, the number of moles has to go up as well in order to keep that pressure constant. Okay, so now let's look at two more. So Charles's law and Gay-Lussac's law. So in Charles's law, we can see that N and P are going to be constant, and again, R is always constant. So in this case, the ones that change are going to be volume and temperature. Okay, so again, you can see that the volume changed in my two drawings. So let's look and see what happens here. I have my 4 moles of gas that are moving around. So now I increase the volume. And again, we want to keep the constant pressure. So what do we have to do in order to keep a constant pressure on the outside of that wall? Well, in this case, we cannot add more gas molecules because the number of moles is going to be constant. So we can only change the temperature. So in this case, do we want the temperature to go up or do we want the temperature to go down? Well, by increasing the temperature, those particles are going to move more. Okay, so now they're going to be like this, but by increasing the temperature, they're going to move faster, which is really hard to draw here, but you can see my scribbling with the pen is supposed to indicate that they're moving faster. And by moving faster, they're going to hit the wall, they're going to rebound, and then they're going to hit the wall somewhere else more frequently, which is going to lead to that pressure staying constant. So in this case, again, it's a case where they're directly proportional. Volume goes up. So volume goes up. Pressure. Whoops, sorry, not pressure. Temperature. Temperature goes up. So again, these two are going to be directly proportional. Okay, the last one over here, Gay-Lussac's law. So Gay-Lussac's law says you have a constant number of moles of gas and a constant volume. So that means the ones that are going to change are going to be the pressure and the temperature, P and T. So notice that in this case, my two circles are the same size, right? So the two circles are the same size, so we have a constant volume, and we're also going to have the same number of moles of gas. So here we have our 4 moles of gas, right? This is our initial conditions. Okay, so now what are we going to do in terms of pressure and temperature? Well, in Gay-Lussac's law, we have to keep the amount of gas the same and the volume the same. So let's say that between the two, that the one down here has increased pressure. Okay, so this one is going to be like a pressurized one. So what that means, if it has more pressure, that means those molecules have to be moving around more, right? So how are we going to get those molecules moving around more? Well, we're going to increase the temperature. So just like we did in the last one, If we increase the temperature, they're going to bounce around more. And I'm trying to draw it a different way, but you get the idea here, right? So by increasing the temperature, they're going to bounce around more, and it's going to cause an increase in the pressure because the volume is now fixed. So again, here if the pressure goes up, the temperature must go up. So again, they're going to be directly proportional. Now, for all of these that I've done increasing, right? Volume goes up, temperature goes up, pressure goes up, temperature goes up. Same thing would happen if they were decreased. So if in this case for Gay-Lussac's law, if the pressure went down, the temperature would go down. Right? If the temperature were to go down, the pressure would go down. All right, so that's how these gas laws work. So the last thing I want to do in this kind of part of working with this ideal gas law, which is this PV equals nRT, is to say that in addition to just kind of thinking about the relationships, which is what I was trying to do in those previous descriptions, you can also approach this mathematically. So for instance, in Boyle's law, that's where, so Boyle's law is when N and T are constant. So in that case, when N and T are constant, N is constant, T is constant, R is always going to be constant, okay? So that means that pressure times volume has to equal a constant, right? Because N times R times T, none of them are changing, so it's going to be constant. So that means that if you were to change your pressure, or you were to change your volume, it doesn't matter in the overall system what happens because it's going to be constant. So in other words, if the pressure goes up, right, the volume has to change in order to keep it a constant. So what we do here is we say P1 V1 is equal to P2 V2. All right? So that is Boyle's law. We say P1 V1 equals P2 V2. So the idea is that the pressure times the volume is always going to equal that same constant. So because of this, saying P1 V1 is a constant, if P2 times V2 is equal to the same constant, we can then say that P1 V1 has to equal P2 V2. All right? So whenever you have an equation that looks like this, right, this one means that they're also going to be inversely proportional. In other words, the pressure goes up, the volume goes down. That's what happens whenever they're on the same side of this equation. So now let's look at kind of a different example. So let's go, we'll do Charles's law here that had constant N and constant P. So we're going to look at volume and temperature changing. So let's do constant N and P. So again, this is Charles's law. Okay, so in Charles's law, N and P are going to be constant. So let's go in here and kind of change this. So N is still going to be constant, R is still going to be constant, but now we also have P constant. So what I can do is rearrange this equation. So instead of saying PV equals nRT, what I want to do is get all of the things that are constant on the same side. So I'm going to divide both sides by P. So I can say V is equal to nRT over P. So I just divided both sides by P. And then the other thing I can do is because T is not constant, right? This T is not constant. I want to get rid of it, so I'm going to divide both sides by T. And I can say V over T is equal to nR divided by P. So now, N, R, and P, these are all things that are constant, right? N's constant, P is constant, and R is always constant. So I can say nR and P is equal to a constant. So that means if I were to change my volume or my temperature, the constant that it equals to has to be the same. So I can say that V1 over T1, like in initial conditions, is equal to a constant. And then V2 over T2 has to equal to that same constant. So therefore, what Charles's law is actually, the way Charles's law is actually written, oops, it says V1 over T1 is equal to V2 over T2. And whenever you have an equation like this, wherever there's one divided by the other, right, V divided by T, that means if one goes up, the other has to go up. So you can do this derivation for all of your laws based on this PV equals nRT equation. And the gist of it is, if they're on the same side, so let's say you know the only two things that are changing are pressure and volume. If they're on the same side here, they you write them right next to each other like you do here, PV equals PV. The rest of them are all on opposite sides. So how do pressure and temperature relate? Well, they're on opposite sides of the equation, so that means they're going to divide. In other words, if one goes up, the other has to go up. So you would have P divided by T equals P divided by T. Or you could say V divided by N is equal to V divided by N, because they're on opposite sides. So again, remember that R is always going to be a constant, and then the other ones, if they're on the same side, they're going to be inversely proportional, and they're going to look like this. If they're on opposite sides of the equal sign, right? So if they're on opposite sides of the equal sign, so P to T, for instance, then they're going to be they're going to be directly proportional. One goes up, the other goes up, and you write them as a fraction like this whenever you do your equations. So just going back again to look at all of these, you can see that P1 V1 equals P2 V2 is the only one that you really multiply, and then the rest of them all divide. And the only one that I didn't really talk about is this combined gas law, which basically just takes PV and T and relates them all to each other. So in this case, N and R are the only things constant, and you say PV divided by T equals PV divided by T. All right, and we'll do some practice problems with these in subsequent videos.